All right. I'm David Gordon, and doing the Computational Materials project. You're going to introduce yourselves real quick.
I'm Nami Uchida.
John Alvarez.
Thank you, Reynoso.
Hadiel Darwish.
Okay. So pretty much we are just looking for new semiconducting materials to use in computer chips, phones, computers, etc. We use a code called Wine2K, which takes two elements, figures out their electron configuration, and then figures out the electronic behavior based on that electron configuration. It solves the Schrodinger equation from the ground up using algorithms, and we are looking at two different systems, the iridium gallium system and the iron gallium system. Now I'm going to hand it over to a new member to talk about some theory.
So hi, my name is Nami, and first we're going to talk about the atomic structure. So the electrons that are furthest from the nucleus are called the valence electrons, and its weaker charge makes it easier to interact with other atoms. That's a unit cell, which is just a group of atoms that form basic building blocks of larger material structures.
Okay, so we basically study electrons and their properties, and an important thing we study is conductivity, which is the flow of electrons. And right here, this explains the theory. Right here we have the Fermi level that the electrons have to cross to get to the conduction band. Over here we have a conductor. The labs actually overlap, which makes it a conductor. And right here we have a semiconductor. We have a small gap, and it's small enough for the electrons to actually travel from this band into this band to make the material a conductor. And right here, the gap is way too big for the electron to actually successfully pass from the valence band to the conduction band, so this would make it an insulator. And this is a translation of our theory. Right here, the lines actually represent the bands, and if you see here, the bands are actually overlapping, which makes this material a conductor. And also, those letters that you see over here actually represent the position of electrons inside the unit cell.
Now, this is just another representation of what Hadiel just explained, and it's called the density of states. In this representation, we can see the valence band here and the conduction band here, and the Fermi energy level just in the middle. How we measure the conductivity of an electron is by looking at the line in the Fermi energy level, and if the electron goes to 0 at that specific point, it's an insulator. Now, if it passes through that point and it's not 0, it's a conductor. So if the gap is not that big, like in here, you see that this is an insulator. That means that we can put a little bit of energy so that it passes through and it's not 0. So we can control the conductivity and make it 0 and not 0.
So updates from the winter, we focused on iridium gallium 1 and 1. We did 1, 2, and 1, 3 over the winter and looked at the electronic structures, but we picked this one because it has something called the Dirac point. If you look where that arrow is pointing, that's a point. So the electrons right here are moving way, way, way faster than these electrons, like almost the speed of light. So you need new equations to describe them, and it makes it so that this material might be part of a new family of materials called topological materials, which are only 5, 10 years old. And this specific subset of them, there's only 6 of them that exist. So to be able to say we can add a new one is huge. But to do that, we have to figure out everything about the Dirac point and how it exists and why it exists, and talk about it in terms of the math that defines it. And that other term I will talk about in a second, but let me just keep going with the Dirac point. So right here, we can actually select a specific path inside the structure for our software to look at, and let us know what's going on right there. So this right here, this corner, is called the R point. And now if you see, when I ran it with that structure, the point actually moved over here, so you can see it's right near the R point. And this is actually the middle of the structure, so we know it's along this line somewhere, which has certain symmetry properties, which we can use to go back to the math and describe, not only show people, hey, this is a Dirac point, but say, this Dirac point has to exist because of all these symmetry operations and things like that. And one other thing we can do, and which we'll be looking for, is which electron orbitals actually are making up these two bands, because that will just add more evidence to our assertion that there is a Dirac point in this material. And the other thing, band tuning, that was on that other slide, is basically showing how the electron structure changes depending on the pressure. Now, if you took physics or chemistry, you know pressure is related to the volume. So all we have to do is we have to shrink our unit cell down by little increments and rerun our simulation over and over and over again and see how the electronic structure changes depending on the volume. And here's a little example. So at a 1% reduction, you see the band is a little bigger than here. At an 8% reduction, so that gap actually shrunk down, and that's something that we can plot versus volume and eventually versus pressure, which is what experimentalists who read our paper will want to know about.
For advances in the iron-gallium binary system, in the winter we discovered that the iron-gallium-3, when we studied the bulk, that means like we would have a big piece of iron-gallium-3. It's basically a semiconductor, like we explained before. This is the little band gap that we see here. Now, if we just cut a little layer of that big bulk material, we get totally different answers. Even though they're the same material, but if we just cut one little slice of it, it's totally different. Here we have a semiconductor, and here we have a conductor. Based on this, we're still trying to investigate what is happening with this. Why just one layer of this is totally different compared to the whole thing. Also, we could check that also in the band structure. As you can see here, there's no band crossing the Fermi level, and over here there is some bands over here crossing. So this is very interesting. We're trying to still investigate why this is really happening. And with the iron 3 gallium, we have three phases. One, the normal points, one with the spin polarization up and spin polarization down. Here in the normal one, we can see the sharp peak here at the Fermi level. This means that this is an unstable material. That means that there are a lot of electrons there, and they're just moving right there doing nothing. But now, if we apply spin polarization up, that means that we make all the electrons spin up. We get a very stable here around the Fermi energy level. And if we apply all of them that spin down, we also get a very stable energy level here. That means that this material has a ferromagnetic nature, basically. And we also could determine that with the band structure. Is it? There we go. Also here with the band structure. As we can see here, we only have some few bands here crossing Fermi level energy. Here, when we apply the spin up, we have more crossing here. And when we apply the spin polarization down, we have even more bands here crossing. So our future goals for this is basically for the iridium gallium, identify the rack points in the iridium gallium, and identify effects of band tuning of this. And for the iron gallium is to identify which electrons and which bands they are crossing from the valence to the conduction band, and identify a reason for why the pressure changing in the bulk material to the layer, why is it happening this? That we have it basically from a semiconductor to a conductor, even if they're the same material. And with all this research, our final goal is to publish a paper in Elsevier, Computational Materials Science Journal.